VR gloves have been around for a long time. The first pair came around in 1982, called the Sayer gloves. They used flexible tubes along the fingers and light sensors. They shined light from the top of the tube, and the light sensors could tell how much light had made it to the end. The bigger the bend, the less light could make it to the fingertips. Although not fiber optics, this technology worked with a similar principle. Since then, we've seen huge advancements in the technology that powers these gloves. More recently, a TikTok user, Lucas_VRTech, has been sharing his journey creating a pair of gloves from scratch. One commonality through all of these gloves that we see is soft technology. That is technology that can move organically and has no hard parts. Lucas on TikTok has been challenging this and uses spring return potentiometers attached to his wrist, rolled with string, which is then tethered to his fingertips. This is straying away from the soft tech trend, but is still taking an approximation of all of the knuckles in his hand as opposed to capturing individual joint movement, which is a main goal of this project. Nowadays, the sensor most common in these gloves, homemade or commercial, is a flex sensor. Personally, I'm not a huge fan of them. I've experienced a high rate of failure and have all but completely removed them from my projects. I decided that I wanted to use hard tech and force it to work as soft tech, which was not a small feat. I also wanted to ensure that I could capture individual joint movement, something that isn't possible with a single flex sensor. After hours of research, I landed on the Borns 3382H. It features a tiny body and has a pinhole as opposed to a shaft like most hobby potentiometers. I came up with a basic design of a case for these variable resistors with an arm that extends back to the previous one and attaches to the pinhole on that. When the finger is bent, it would sense the change in rotation on the previous knuckle and translate that into movement. This basic idea persisted until my final version. I then translated it into CAD and printed it on my Elegoo Mars 2 Pro. This was a bad start. I knew I would just be making one finger for this assignment, and this was the easy and lazy way out. A design that would only work for one finger, since I clearly can't put this between each finger or you couldn't close your hand. I decided that this wasn't good enough and began to redesign. Most VR gloves use a system mounted to the top of the hand for good reason, and this quickly became the obvious way to go. The other issue with this first design is that when you bend your finger, the distance between your joints lengthens, or at least the distance between potentiometers does if they're mounted perpendicular from your finger at each joint. A rigid design like this just wouldn't work. I thought about a rod and collar design, where one side was a rod and the other a tube, allowing the rod to slide in and out. Friction was a problem with this design, because I wanted to feel as if there was nothing on your hand at all. The biggest, most worrisome part, though, was that the parts were getting extremely small and detailed. In general, your design should have as few moving parts as possible, and this was not following that design rule, so I didn't even bother printing this version. I then began thinking about using a living hinge, which is a moving part made of the same material as the things it connects. I printed the bands between the potentiometers at 2 millimeters, which seems to work perfectly. The bands are curved to avoid any interference as you bend your fingers. The piece you see on the back of the hand is what I call the hand guard. It houses an Arduino Mega 2560 Pro, an extremely small form factor Arduino Mega with a footprint of 3 by 5 centimeters. Although this version could have been run off of something as simple as an Arduino Nano, I wanted the ability to add the rest of the fingers as well as haptics and force feedback in the future. Finally, you can see the entire thing working interfaced with Unity using a Unity add-on called Uduino. This made the connection extremely easy by allowing you to access pin input and output directly in your Unity C# script. This code is extremely simple and is pulling angle information from the potentiometer. For the second potentiometer, it is not only rotating locally, but also rotating the entire cube around the first cube, compounding the movement from both sensors. My project went through a very interesting transformation. It began as what I thought would be a technical challenge, turning sensor information into accurate movement in digital space. By the end of it, however, I discovered it to be an exploration of human movement. The true challenge ended up being figuring out how to allow organic movement to occur. While my version 1 would have worked as a one-finger motion capture machine, it didn't allow me to move as naturally as I would have wanted. The purpose of this project was to capture three-dimensional movement. What I realize now, however, is that if the method of capture infringes on the movement it is trying to capture, the project at its core has failed. This brought me to really try to understand how the hand moves. The angles, the distance between joints in relation to the amount the finger is bending, and bilateral movement are all extremely important factors. I began thinking about human-centered design. This is something talked about constantly in my workplace, but I hadn't introduced into my personal workflow. At every step in the problem-solving process, the first question you have to ask is how will somebody interact with this?